Welcome, clinical research innovators, to a transformative exploration in our machine learning series. I'm excited to lead you through this episode, where we'll tackle a classification challenge using a critical dataset and a cutting-edge explainability tool. I'm working in Google Colab, guiding you through each step with clarity so you can follow along as we classify breast cancer diagnoses with precision. Let's dive in by setting up our environment and assembling our tools for this precision medicine study. I begin by installing the Interpret library in Colab with a quick pip command. This library will empower us to explore explainable AI, helping us uncover the reasoning behind our model's decisions. Next, I import the essential tools. NumPy for numerical operations, and from Sklearn, I bring in Load Breast Cancer to access our dataset, Train Test Split to split our data, Random Forest Classifier for our model, PCA for dimensionality reduction, and Pipeline to streamline our workflow. From Interpret, I import Morries sensitivity from the black box module, our tool for global explanations, along with the show function to display results. I set up inline visualizations with set visualize provider and inline provider, ensuring our plots render seamlessly in Colab. I also set a random seed to 42 using NumPy's random seed for reproducibility. With our tools in place, let's load the data. I load the breast cancer Wisconsin dataset using Sklearn's load breast cancer function, with return XY set to true and as frame set to true to get features and target as data frames. The dataset contains 569 samples of breast cancer tumors, with 30 features like mean radius, worst area, and worst symmetry, derived from digitized images of fine needle aspirates. The target is binary, 0 for malignant, 1 for benign, with 212 malignant and 357 benign cases, making it a binary classification task. I split the dataset into training and test sets using Train Test Split, allocating 20% for testing and 80% for training, with random state 42. This gives us 455 training samples and 114 test samples, roughly 43 malignant and 71 benign in the test set, based on the dataset's 37 to 63 split. The features are all numeric and there are no missing values, so we're ready to build our model pipeline. I create a pipeline to combine dimensionality reduction and classification. First, I initialize PCA, Principal Component Analysis, from Sklearn, which reduces the 30 features into a smaller set of uncorrelated components, capturing the most variance in the data to reduce noise and speed up training. Then, I initialize a random forest classifier with random state 42. Random forest classification is an ensemble method that builds multiple decision trees, 100 by default, each trained on a random subset of the data and features, and combines their predictions through majority voting to classify outcomes, enhancing accuracy and reducing overfitting. I create a pipeline named Black Box Model with PCA and the random forest and call fit on X-train and Y-train to train the model, enabling to learn how transformed features distinguish malignant from benign tumors. I use Morries sensitivity from Interpret's Black Box module to explain our model's behavior globally. The Morries sensitivity method is an explainability tool that measures feature importance by perturbing inputs and observing how these changes affect the model's output. It varies one feature at a time across its range, calculates the change in prediction, the elementary effect, and repeats this process to estimate the mean effect for each feature, with higher values indicating greater importance. I initialize Morries sensitivity with our black box model and X-train as the background data, generate a global explanation with explain global, and extract the feature importance data. The global feature importance scores are worst area 0.1228, the highest, indicating it's the most influential feature for classification. Mean area 0.0834, mean perimeter 0.0608, and area error 0.0571 follow, showing area-related features are critical. Worst radius 0.0521 and worst perimeter 0.0509 also rank high, while worst concavity 0.0125 and concave points error 0.0146 are among the least influential. These scores suggest that size-related features, especially worst area, are key drivers in distinguishing malignant from benign tumors, while features like concavity have less impact. The visualization likely shows a bar chart with worst areas bar at 0.1228, followed by mean area at 0.0834, and shorter bars for worst concavity at 0.0125, providing a clear ranking of feature importance. Let's dive deeper into these outputs. They're a blueprint for precision diagnosis. The global feature importance scores reveal worst area at 0.1228 as the top driver, suggesting that the largest tumor area measurement is critical for classification, likely because malignant tumors tend to grow larger. Mean area 0.0834 and mean perimeter 0.0608 reinforce this, indicating that average size metrics also play a significant role. Area error 0.0571, worst radius 0.0521, and worst perimeter 0.0509 further highlight size and boundary features, which align with clinical knowledge that malignant tumors often have irregular growth patterns. Mean radius 0.0555 is notable, but its lower score compared to worst area suggests that the most extreme measurements are more telling. On the lower end, worst concavity 0.0125, concave points error 0.0146, and mean fractal dimension 0.0150 have minimal impact, possibly because these features capture shape irregularities that are less distinguishing after PCA transformation. Mean symmetry 0.0318 and worst smoothness 0.0279 show moderate influence, indicating some role for symmetry and texture in classification. Morris Sensitivity's global view helps us prioritize features for diagnostic focus, emphasizing size over shape in this context. To wrap up this precision medicine analysis, we've explored the breast cancer dataset, a 569 sample study of tumor characteristics, and trained a random forest classifier within a PCA pipeline, leveraging Morris sensitivity to reveal worst area and mean area as top drivers of classification. Random forest classification's ensemble approach captured complex tumor patterns, and a Morris sensitivity method's perturbation-based analysis provided transparency for our black box pipeline in this binary classification task. Grab this code, experiment with PCA components, and dive deeper into cancer diagnostics. I'm inspired by this clinical insight. Hope it's ignited your passion for data-driven medicine. See you next time for another groundbreaking data exploration.